Hi, thanks for joining me. Today I'm going to be going over problem 6 from the Imperial College Maths competition. As always, there'll be a link in the description below with details of the competition. This is the problem I'm going to be tackling today. It's kind of long worded, but here's the description. So we have this checkerboard, if you want, or just sort of the sequence of squares, and there are n plus 1 squares. So the first one we're labelling 0, then 1, then 2, then 3, all the way up to n. So we've got n squares, and on square 0, initially there are some stones, and the number of stones is k. So we have k stones initially on square 0 only. Now we have this guy Tony playing a game, and Tony wants to, his main goal is to bring all the stones onto this square here, square n. However, each move he can only do certain things. So each move he can only move, he chooses a stone, and that stone he can only move across up to m squares. And what is m? Well, m is the number of squares which are on a square number less than or equal to that chosen stone. So, for example, suppose at some point in the game, let's say there are 2 stones here, 2 stones here, and maybe 1 stone there, then Tony, say, chooses this stone here. Okay, so the number of stones that are less than on a square less than or equal to that stone is 1, 2, 3, 4. So this stone can move up to 4 squares across. So it could go up to 2, 3, and then 4, and then 5. Okay, so that is what's known as a move, and Tony's goal is to bring all the stones onto square n. We want to prove that it must take at least n over 1 plus n over ... plus n over 3 plus ... plus n over k moves for him to get all the stones onto square n, remembering that all the k stones start on square 0. So this thing here is precisely n times the kth harmonic number. Anyway, we want to prove that it takes at least that number of moves. So if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so there are a few different ways you can solve this problem, but the way I'm going to show you is hopefully the easiest to follow. It's not the easiest to write down, so I'm going to try and explain, as best I can the bits that I'm doing. But yeah, let's get stuck in. We're going to define t to be the total number of moves. So of course our aim is to show that t is at least n over 1 plus n over 2 plus n over 3 plus ... all the way up to n over k. Now we have, what I'm going to do is give an example in just a second. But what we want to do is Tony's going to take a bunch of moves to get all the stones from the initial square to square n. And each move, what we want to do is give a score to in a fashion which I'm going to describe just now. So each move we're going to give a score to, and then what we're going to do is build some inequalities involving the scores, and then that will give us the desired result. Okay, so it's quite difficult to explain, write out word for word how we're defining this score. So what I'm going to do is just give an example or two. So suppose Tony's done a few moves, and he's now with this setup here, and he's about to take a move, and he chooses this stone here. Okay, well notice that there's 1, 2, 3 stones less than or equal to it, so he can move it up to 3 stones across. So and let's say, suppose he wants to move it exactly 3 stones across, so he goes 1, then 2, and then finally 3 squares across. So this is his move for this stone, and what we want to do is calculate the score of this move, and this is how I'm going to do it. So the score S of the move M is going to be this thing here. So firstly, I'm going to take the reciprocal of the number of stones less than or equal to it to start off with. So there's 1, 2, 3 stones less than or equal to it. So firstly, I'm just going to have a third. But then I'm going to add on something else. What am I going to add on? Well, once this stone moves sort of 1 square across, let's put it here. I'm also going to add on another reciprocal. So 1, 2, 3, 4, 5, 6, 7. So I'm going to add on 1 over 7. Okay, and then now this stone moves to this square here. So now I'm going to add on 1, 2, 3, 4, 5, 6, 7, 8. So 1 over 8. Okay, and then that's it. Then the stone goes here, and I'm done. So that's the score of this move. It's a third plus a 7th plus an 8th. Okay, and one thing to notice is that a 7th is less than a third, and an 8th is less than a 7th. So in particular, this thing here is going to be less than a third plus, or less than or equal to a third plus a third plus a third, which of course is 1. And in fact, this thing holds for every single move. So the score of any move is less than or equal to 1. So when we add up all the scores of all the moves, we're going to get that the sum of the scores, so let me just write it like that. That thing there is going to be less than or equal to the sum of the moves, because for each move, we know it's bounded above by 1, so 1 times the sum of the moves, but we know that this thing here is just t. So we've got that t is greater than or equal to the sum of the scores of the moves. So now if I can show that this thing here equals n over 1 plus n over 2 plus dot 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 plus n over k, then I'm done, because then I'll have that t is greater than or equal to the thing that we want to show. So that's what I'm going to do now, is show that the sum of the scores must be equal to n over 1 plus n over 2 plus dot 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 all the way up to n over k. Let's do that. Okay, so now what we want to do is show that the sum of the moves, the sum of the scores of the moves, must equal n over 1 plus n over 2 plus dot 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 all the way up to n over k. And the way we're going to do that is focus on the first n squares here. So the squares 0 up to n minus 1. Now, have a look. Let's take any of these squares. Let's say square 4. Now, once Tony has achieved his goal by bringing all the k stones to square n, what he's going to have done is brought every single stone through each of the squares here, all the way up to square n. So any particular square, let's say square 4, each stone has got to travel sort of onto it, but then off of it again, and that applies to every single case, every one of the k stones. Okay, now let's look at square 4. Well, there's going to be some sort of order of arrival of the stones, and it doesn't really matter what the order is, but each stone is going to have to go like this, and then out again at some point. They might be in 2 separate moves, that doesn't really matter, but notice that for each stone there's going to be some sort of score, or in the score there's going to be some sort of 1 over I, where I denotes the number of stones less than or equal to that thing there. But sort of for the first stone that gets there, the 1 over I will be precisely 1 over k. Okay, then for the next stone that arrives there, we'll get a 1 over k minus 1, because obviously the stone that gets there first will have moved on forward. So when the next stone gets there, it's going to be 1 over k minus 1. Then we're going to have a 1 over k minus 2, and so on, all the way down to 1 over 2, and then 1 over 1. So the 1 over 1 is for that last stone that gets there. Okay, so this is in some order. When we sum up the scores, there'll be a 1 over k in there, 1 over k minus 1, and so on, and 1 over 1, all sort of corresponding to the stones going through this square here. But of course that applies to absolutely every single square between 0 and n minus 1. So when we sum up the scores, we're going to get this thing here. But obviously one of these for each square, so we're going to get n lots of those. Okay, so the sum of the scores, sum of the scores of the moves is equal to this thing here, which is precisely what we wanted to show when we bring n inside the bracket. Okay, so as I said, it's not the easiest to sort of write down pen on pen and paper sort of thing, but hopefully I've explained it well. Just for this part here, remember that each stone has to go through these first n minus 1 squares at some point, and then of course for each square there's some sort of order of arrival, and then from that we get this thing here. But this applies to each of the first n squares, so square 0 through squared n minus 1, and that's why we get this factor of n out the front, and we've shown what we wanted. And then of course this thing here is less than or equal to the total number of moves, t. Okay, I hope you have enjoyed this video. It's quite a cool solution and quite a cool problem. But yeah, that's all for today. I will catch you in the next one. Have a great day.